This lecture is about extensions to the simply typed lambda calculus. So this is the abstract syntax for the simply typed lambda calculus that we studied so far. So for types, we have this base type and function type. And for expressions, we have variable, lambda abstraction, and application. And of course, this base type can include, for example, Boolean and other base types. And in that case, we have to extend the set of expressions. So for instance, for Boolean base type, we'll include true, false, and if then else, and so on. Now, we'd like it to extend this simply typed lambda calculus with the new types. Specifically, we'd like it to introduce product types, which we write as A product A. Product types is like A times B. And we are also going to introduce sum types, which we write A plus B. So here we are going to have A sum type A. And finally, we are going to introduce fixed point construct. The product types are what we need to implement tuples or pairs, records, or even unit in functional programming. And some types are something like disjoint unions. And fixed point construct is a primitive construct that we introduce to support recursion. So for each category, we are going to extend the syntax first, and then we are going to give typing rules, and we are going to give the reduction rules. So for product types, we are going to extend the syntax with this product type and corresponding new forms of expressions, and then we will study typing rules, and we will formulate their reduction rules. And similarly for sum types and fixed point construct. So let's first talk about these product types. So product types. So the idea behind the product types is if a value v has a product type a1 times a2, it contains two values. It contains two values, the first of type a1 and another value of type a2. So it always carries two values. That's the idea behind the product types. So for syntax, we are going to use pair. So we write pair E1, E2 enclosed in parentheses. So this pair basically pairs of two expressions, E1 and E2. So if E1 has a type A1 and E2 has a type A2, probably we will assign type A1 times A2 to this expression, this pair. So this is called the product type, which indicate the presence of this times indicates that we carry both value of type A1 and also another value of type A2. So that's the basic idea behind the prototypes. And for expressions for prototypes, we also need we also need what can be called the dual to this pair. So this pair expressions allows you to pair two expressions, E1 and E2. And we need the dual operations. That is, suppose that we have an expression of type A1 times A2. Probably we will be able to extract two components from this expression E. So we need two operations for extracting the first component of E and the second component of expression E. So to this end, we introduce two projections, which we write first E and second E. So if expression E produces a pair, such like E1 paired up with E2, then first E will extract this expression E1, and this second projection will extract the second component expression E2. So in summary, for product types, we will introduce a new form of types called the product type of this form, A1 times A2. And the idea is we are going to carry two values, one of type A1 and another value of type A2. And in order to create a value of an expression of a product type, we use a pair of this syntax. So this allows you to create pairs or expressions of this product type. And the dual notion is we need to be able to extract individual components from this pair. So we need these projection expressions, first E and second E. So that's the informal introduction to product types. Now let's formalize this idea with concrete syntax and typing rules and reduction rules. So this so product types. So this is the syntax. First, types. We needed to extend the definition of types. So we carry everything from the previous definition of simply typed lambda calculus, and we add a new component, A times A. And expressions now include everything developed so far and its pair and projection, two forms of projection, first E and second E. So that's the syntax. Then what about typing rules? So this is the syntax. And what are the typing rules? Let's try to develop this typing rule for this pair. So our intuition says expression E1 is going to have type A1, and expression E2 is going to have type A2. Then we are going to assign type A1 times A2, this product type. So that's the idea. So let's turn this informal idea into this formal typing rule. We require that expression E1 should have a type A1 or some type A1, and expression E2 should be also well typed. We should be able to find an appropriate type here. Then we can assign A1 times A2 to this expression pair. And like the function introduction rule, arrow introduction rule, we give this name times this product introduction as the name of this typing rule, because if you read this rule top down, you end up introducing these times. So this I stands for introduction. So that's the name of this typing rule. And what about the typing rules for these two projections? So probably this expression E is going to have a type, a product type, something like A1 times A2. Then the whole expression is going to have a type A1. So we require that expression E should have a type A1 times A2, in which case this projection, uh, these expressions are called the projections. Uh, this is called pair. Projection E is going to have a type A1, and similarly, second E is going to have a type A2, and we call this rule product elimination rule, first case, and this is the product elimination second, because if you read this rule top down, you end up eliminating. This E stands for eliminate. So if you read this rule top down, you end up eliminating this product type times. There is no times here, so it has been eliminated. So these are the typing rules for product types. Now let's develop the reduction rules. So reduction rules for this pair construct and projection is two forms of projection. So we can think about two alternative strategies. There is eager strategy, and there is also lazy strategy. In the case of eager strategy, given expression E1 and E2, we are not quite happy about the form of this expression, so we'd like to eagerly evaluate this expression E1 to produce a value. So in other words, this pair is not a value unless these two expressions E1 and E2 are both values. So in general, this one is not a value, and therefore we'd like to keep reducing the two components inside these parentheses. So that's the basic idea. So for example, if expression E1 reduces to another expression E1 prime, this one will reduce to this one to this expression if expression E1 reduced to E1 prime. So that's the basic idea behind this eager reduction strategy. In the case of lazy strategy, we just take this pair as a complete form of value. This is counted as a value. That's the big difference from this eager strategy. So again, in the case of eager strategy, we don't regard this pair as a value unless both expressions E1 and E2 are already values. In the case of a lazy strategy, we count this pair as a complete form of a value, so there is no further reduction. Let's develop the reduction rules under this eager strategy. So first, suppose that expression E1 is further reducible. If this guy reduces to E1 prime, this is not a value, so we keep reducing it. This time, it's going to be E1 prime, E2. So we have the first reduction rule. And if everything goes okay, this expression E1 eventually turns itself into certain form of value V1. So in that case, we have V1 expression E2. Now suppose that expression E2 reduced it to E2 prime. Then we reduce the whole pair into V1, E2 prime. So if everything goes okay, this expression E2 will also produce another value V2, in which case we generate this value V1, V2 paired together. So in the case of eager strategy, we extended the set of values, the syntactic category values now include a value paired with another value. Let me erase this one. So that's the eager reduction strategy, the definition of values under the eager strategy. Now, what about the projections? Suppose that we have a first E. In general, this expression is another value, so E could be reduced to another expression E1, E prime. In that case, we reduce the whole projection into this first E prime. And if everything goes okay, this expression E will eventually produce a value. And if this is well formed, probably the form of the value from this expression E will be a pair of values. So if everything goes okay, we will produce something like V1, V2 paired together. In this case, we just take the first component. It's going to be V1. And the case for this second projection is completely symmetric. Now let's consider the reduction rule. These are the reduction rules under eager strategy. And what about lazy strategy? In the case of a lazy strategy, we take this pair of expressions as a value. So this is counted as a value, regardless of the forms of individual expressions inside the parentheses. So under the lazy strategy, the values, the definition of values extended with this one. So the definition of values include this one as a new component. Then what about the reduction rules? So first, notice that there is no reduction rule for expression E1 paired up with expression E2, simply because it is already counted as a value. So there's no further reduction. It's already value. Then what about first E? So there's no reduction rule here. So in general, we should be able to further reduce this expression E. So if this rule reduces to E prime, then first E reduces to first E prime. And if everything goes okay, this expression E will produce a value of this form. So eventually we will have something like E1, E2. So this is actually a value under this lazy strategy, at which point we simply extract the first component. And of course, the expression E1 is not going to be value in general, so we should be able to further reduce it. And for this second projection, we also have a similar pair of rules. So these are the reduction rules when we choose lazy strategy for pairs. So for product types, we extended the syntax with these product types with the pairs and two forms of projections. And for typing rules, we have this product type introduction rule and product elimination rules. And for reduction rules, we can choose either eager strategy, in which case we have these reduction rules, or we could choose lazy strategy, in which case we have these reduction rules. Now, let's talk about generalized prototypes. The idea is that we have this prototype, but the thing is there's no reason to stop at number 2. There's no reason to stop at prototypes dealing with only 2 components. We can easily generalize with multiple components where the number of components n is going to be greater than or equal to 2. So if, as a special case, if n is 2, then we obtain the previous prototype, a1 times a2. So it's pretty easy to generalize these prototypes by allowing multiple components, multiple types inside this prototype. So n is, of course, 2 is allowed for n, but n can be greater than 2. So this is the idea behind the generalized prototype, where now we are carrying n different components at once. And it's also easy to extend the syntax for expressions. Previously, we put 2 expressions inside these parentheses because we allow only 2. Now, we can have 2 or more components in this generalized prototypes. So we can enumerate E1, E2, and different expressions inside these parentheses. So that's the idea. So, for instance, if expression E1 has a type A1, expression E2 has a type A2, and expression En has a type An, then probably this expression will have this product type, generalized product type. And for historical reason, this new form of expression is called tuples. And now we needed to introduce another form of expression for extracting components of these tuples. Just like for pairs, we have 2 projection operations, first E and second E. Now we allow multiple components inside the parentheses. So we also need to generalize these projections. So we write projection I expression E, where the idea is we are going to extract the ith component from this expression E. So probably this expression E is going to produce a tuple of this form. And this projection I is going to extract its ith component. So that's the idea. So here, I is found in this range. So it's a simple generalization of the previous product types with the 2 components. The difference is that we just allow multiple components in product types. So in some sense, we can say that we are talking about the generalized n-ary case as opposed to binary case. If n is 2, then it's going to be binary case. And now we generalized it, so n can be any integer greater than or equal to 2. So we are talking about this n-ary case. So that's the idea of how to generalize the product types. And it's pretty easy to derive the typing rules and reduction rules. So let's just consider typing rules. So what would be the typing rule for this tuple expression E2 expression en. So the idea is expression E1 has a type A1, expression E2 has a type A2, then it's going to have type A1 times A2 product AN. So the premise is going to be gamma expression EI has a type AI, where I is found in this range. So that's it. This is generalized product introduction type. And it's also easy to define the typing rule for this projection. So what is the type of this projection I expression E? In order for this expression to have a valid type, probably expression E must have valid product type A1 times A2 times AN. Then we are going to extract the ith component. So it's going to have type AI. So this is a product elimination rule, generalized. So this is how we generalize product types. Remember that this one is dealing with this n-ary case as opposed to the previous binary case. So previously we talked about this binary case. This case deals with this n-ary case of product types. Now there is an interesting question. What happens if we set n to 0? So the question now is, what happens if n is set to 0? So we are actually talking about a nullary case. So let's go back to this generalized typing rules. I'm going to set n to 0. So this is n-ary case. N-ary case. So we are going to set n to 0. And let's see what happens. First, inside these tuples, we have n components. So if we set n to 0, we have 0 components, which means that when I set n to 0, all these individual components inside disappear. So we are left with just parentheses. So this is the syntax that we find when we set n to 0. And what about this projection? This projection allows us to extract the ith component, where I is found in this range, from 1 to n inclusive. Now let's set n to 0, then what happens? So this becomes 0. And this one means that there is no such I satisfying these inequalities. Intuitively, there is no component inside these parentheses. Therefore, there is nothing to extract. We should not be able to extract any interesting component from this one. So it turns out that when we set n to 0, this projection disappears because there is no such I, so no such index. Let's move on to the typing rules. This is the typing rule for generalized product type, assuming n. Now let's set n to 0. So the premise has actually n different cases, from I set to 1 to I set to n. Now n is set to 0. That means that all these individual components inside disappear. So the premise disappears. So everything in the premise disappears. And this one all disappears. And this one also disappears. So, and we use a special new type to indicate that all these individual components has disappeared. So it's type unit. And what about this one? Here, the index I is in this range from 1 to n. And if n is set to 0, there is no such index I that satisfies these two inequalities. So therefore, there is no instance of this elimination rule if n is 0. So this rule simply disappears. So to summarize, we are left with if n is set to 0, that is, we are talking about this nullary case. What happens is this one all disappears and we introduce new syntax, which is unit. And the individual components inside the parentheses all disappear. So we are going to use this pair of parentheses. So this is a new form of expression that corresponds to nullary case of product types. And we have this reduction, this typing rule, which we can rename it to unit rule. And this rule simply disappears because there's no such projection. So when we set n to 0, that is, for the special nullary case of product types, we obtain this unit expression, which should be familiar from functional programming. And it is going to have a type unit. And of course, this unit is counted as a value because there's no further reduction here. So to summarize, if we set n to 0, that is, in the case of for this nullary case, we obtain unit and unit type as a special case of generalized product types.